to episode 2 of Rates of Reactions. I will continue where we left off. Now, just relax on what you just learned. I know it's, yeah, maybe for now it starts off as like, oh, it's easy, whatever, but I just wanted to do this quick revision because I know some people maybe try to understand this at home alone, but yeah, let's just do it together, guys. It will not kill anyone. So yeah, I want us to learn about two types of reaction, two types of any reactions. And I know, I don't know why reactions are gonna pull more. It's reactions, right? Now we have the first one, not the reactions that you're thinking about. You have the exothermic and endothermic reactions. Now, here we are going to be understanding these reactions. Why? Because I don't want to say exothermic reaction, endothermic reaction, then someone comes and say, please explain to me what is an endothermic reaction, what is an exothermic reaction. Understand one thing. Exo, just think of exit. Exo, just think of exit. Exit what? It takes out heat. So it releases energy. So understand, an exothermic reaction is a type of reaction. I want you to know that. Yeah, so a type of reaction, a type of reaction that releases energy. Yeah? But angifuni sithi thina energy nje siyishiye lapho. What type of energy? Heat energy. I want you to say that. It releases energy, but not just energy. It releases heat energy. I want my students to be able to say that. Now, if you release a lot of heat, it means more of the energy that we're talking about is released more than it's absorbed, right? It is released more than absorbed. So more energy is released more than absorbed. So every time when you lose something, you become negative. I'll come back to that, why it's called negative, but yeah, for now, just keep that in mind. When you lose something, you become negative. If you keep on giving, usalungasana next, meaning you're left with nothing, right? Meaning you become, once you start giving again, even when you don't have nothing, right? When you start giving stuff that you don't even have, you become negative. Because if you remember, I always say that when you say a smaller number minus a bigger number, it will give you maybe -1. Check one thing. This only had two, right? This 2 was only 2, but because it was trying to give away to the 3, right? Give the 3, right? But it ended up getting what? Negative. Oh, that was a bad explanation, but but yeah, just don't worry about it. But I just want us to be able to understand what I was speaking about right there, because I want people to understand the part of negatives, because I will explain about negatives, but I just want you to keep in mind that yes, you are going to be negative or whatever. Now, when you speak of endo, I want you to speak of indoor, right? Indoors meaning inside. Now, this means that it's a type of reaction. It will be the opposite of this one, of course. Type of reaction. Yeah, I never had reaction. I don't know why. Type of reaction that absorbs energy. So if you don't release, you absorb. The type of reaction that absorbs energy. That's what you must know. Now, if here we say that more of the energy is released than absorbed, it means here more of the energy is actually absorbed right here than released. So here we release more than we absorb. In the endo, we absorb more than we release. Indoor meaning inside, So we keep it inside to absorb, to take something in. So indoors, endothermic. I want us to, we can cram this part. No need to worry about that. It's not a train smash. As long as you're able to understand it, that's my aim, that people understand what I'm talking about. Now, that's all you need to know for now. I want us to do a few graphs. Now, let's do the first graph for an endothermic reaction. Now, the first graph we're going to do is for an endothermic reaction. Now, an endothermic reaction, right? Now, what type of graph is this one? Just know that they call it the potential energy. Potential energy versus, they will ask you to draw this, by the way, sometimes, versus the reaction progress, right? They won't ask you the name, but they'll ask you to draw it sometimes, right? In chemical equilibrium, they'll ask you. In rates of reactions, they might ask you, right? So please be careful of that one. So you must be able to know that. Now, exothermic reaction. What we must know is that, of course, there's a random graph in J. We must have the x-axis and the y-axis. So now the x-axis will be the reaction progress, right? Will be the reaction progress. We'll be measuring using the y-axis. There's no values here. Don't worry. There's no values there, right? Then here we have something that, okay, how do I say this? Potential energy. Now, potential energy, we know here it's measured in kilojoules. That's the potential energy. So remember, it's potential energy versus reaction progress, and I'll explain what is going to happen. Now, check. The potential energy of the system will start here. We're speaking about a system that is an endothermic reaction. So let's just use a different color. Let's use red, right? Now, check over here. Let's say, for example, you start your reaction over here. Right? Now, if you remember, we said an exothermic absorbs. So an exothermic absorbs. So that means that at the end, we must have more energy than what we already have, right? So again, it will start by that. Then something happens. It absorbs energy, it absorbs energy, it absorbs energy, it absorbs energy, it absorbs energy. Eventually, it can't absorb anymore. It's full, and then it stays stable again. That is exactly what happens in an endothermic reaction. Now, but check one thing here. I want us to check one thing over here. Do you see that over here on this part? Right? On this part. You must know that that part over there is called the energy of the reactants. Because at the start of the reaction, you have what? Reactants. Right? And then after that, you absorb the energy to form what? The energy of the product, right? You react to form product. That's just that, right? Now understand one thing. The energy that you need for you to even form the product is also called the activation energy. It's just the activation energy. We've been talking about it. But you see this point over here. This point, that peak over there, you can call it a peak, is fine, because I see a peak also. I don't know about you, but here, this is a peak. This is a peak. Now, that point, you must be able to identify as the activated complex. Now, if you do maths, you'll understand which this here is the turning point. Why the turning point? This is where it's unstable. Right? This is where reactants convert to product. So over here, our reactants, they were absorbing the energy. Not apparently, but eventually they get to that point. They were like, okay, now we have absorbed so much energy to form product. Let's form the product. And then they decrease to form the product, and they become stable again. Now, this is what happens. This is just a course or reaction progress. This is what essentially happens in a reaction. You start off with product, in an endothermic reaction, because in an endothermic reaction you absorb the energy, so you're going to absorb it. If you absorb, it gets more. And if you absorb, it gets what? It gets more. So you absorb the energy, as you see, the energy that you start with, which I want to make a statement of, the energy that you start with is not the same as the energy that you get to the activated complex with. But the energy from where you start to the activated complex, we call that the activation energy. I just said that, right? We call that the activation energy, because this was the minimum energy that you needed for you to then be able to say, I can react to form products. If you're reacting, if it's a chemical reaction, something must be formed. You can't say, this is a chemical reaction and nothing is being formed. No, you must form something. So as soon as you get to the activated complex, it's when you are able to say that, oh, now I can form my products. I have absorbed so much energy, I am able to form my products. But remember, what were you trying to meet by absorbing this energy? You were trying to meet the activation energy. That's what you were trying to meet, right? So after you've met the activation energy, you then turn to form what? Your product, and then you stay stable again. That's exactly what happens. All right, now understand. Now the energy from the product's energy to the reactant's energy, we call that the enthalpy, or the change in we can call it the change in enthalpy, or maybe you can call it the heat of the reaction. Yeah, there's a lot of schools, different things, different textbooks, different people who teach it different ways, but just know from grade 11, grade 10, we call this the enthalpy change, the heat of reaction, if you want to say so. Now that basically means that it's the energy absorbed or released during a chemical reaction. So during you look at the system, right? We say that this heat of enthalpy, I said that it is the energy absorbed or released in a chemical reaction. So if you want to look at this, right, in many ways, just know one thing. Let's just do this. You are starting here with reactants. You're putting your reactant in a container, trying to react something. Now you know one thing. You can't just say, this will reaction, I'll just pour in some things, a reaction will take place. It doesn't work that way. You must meet the minimum energy required for that reaction to take place. What is that energy? It is the activation energy. It's the energy from where you start to the activated complex. So from where you start to the activated complex, that is the energy that you needed for you to then transition. Because activated complex, they also call it in some schools, a lot of people that I know, they call it the transitional complex. Why? Because it's where you transition from reactant to your product. So you must be able to see that. So the energy that you take from where you start all the way to the activated complex, where you then change to your reactant, to your product rather, is called the activation energy. The energy you take from here all the way to the activated complex, it's the activation energy, because that was the minimum energy you were required, or you needed, for you to transition from your reactant to your product. But I want you to look at one thing. If, for example, this was 10 kilojoules, and this right here was 100 kilojoules, and then maybe this one over here was 90. Then I want us to remember one thing. Heat of enthalpy, change in general means the final value minus the initial value. But since we are speaking about the change in enthalpy, it will mean that we want the enthalpy final minus the enthalpy initial. But enthalpy is the same as energy, right? It's just the same as energy, right? It's the same as energy. Don't worry. Just because they use the H, don't get because heat is energy, guys, right? So here, if you look at this, check one thing. The H final is just the energy of the products. That's the final result, because After everything you've done, finally you form what? Products. Now check. What is the energy of your product? Your energy of your product is going to be 90. And then what is the energy? Initially, it's just 10 joules. So minus 10 joules. Now you get your heat of reaction or enthalpy change as 80 kilojoules. Now check one thing. You got what? A positive answer. That's what I said, when I spoke about positive and negative. I said that in an endothermic reaction, you become what? Positive. Why? Because you are absorbing more energy. That's why when they represent an endothermic reaction, they will say that the enthalpy change or the heat of the reaction is greater than 0. Therefore, you must know that this over here is an endothermic reaction. That one you must know. It's an endothermic reaction. If the enthalpy change is greater than 0, if they show you something like this in an exam, you must be able to identify what this is an endothermic reaction, because I just told you if you absorb more, it means that finally your energy is going to be more than your initial energy when you minus them to get the enthalpy change, which is the energy of the react from where you start to your product. The enthalpy change is not from here to the activated complex. The energy from the reactant to the activated complex is what? Is the activation energy. Activated, meaning from energy of the reactant to the energy of the, not the energy, to the activated complex, it's called the activation energy. But the change from the products to the reactant energy, we call that the heat of reaction, or maybe in other schools they call it enthalpy or enthalpy change. It's up to you guys. It's the same thing, right? But now I want us to understand right now, just to consolidate on what I just spoke about just now, so that I can be able to wrap this one up, guys, right? So that I can be able to wrap it up nicely. But yeah, I just want to wrap it up with a little bit of consolidation, so I can make sure that everyone understands the ins and ends of what I'm trying to explain here, because chemistry is a little bit thicker. Yeah, it's hard to explain, but we are going to do it, right? Check one thing. Now, what did we say? We said that in an endothermic reaction, you must absorb more energy, right? So ultimately, you start off with your reactant. After your reactant, you just can't go to products. You must meet the minimum energy of the reaction, that is of the system, for you to have a reaction. That energy is called what? The activation energy. It means it's the energy from the energy of the reactant all the way to the activated complex. It's not from 0 to activated complex. It's from the energy of the reactant to the activated complex. That is called the activation energy, because that is the minimum energy you needed for you to transition, convert to product. Because in the activated complex, reactants can convert to products. Once you have reactants converting to products, or once you form products in a reaction, it means a reaction is taking place. Right? So in this particular case, you are still absorbing energy, because in an endothermic reaction, we could remember indoor, we take in, we absorb. So you are still absorbing energy to get the minimum energy that was required for you to be able to react. If they ask you, what is the activation energy formula? I want you to know this. There's no formula, just I know what it means. The activation energy, just know this. The activation energy is always the energy at the activated complex minus the activation, not the activation, the energy of the reactant. You'll always get the answer. Now check one thing. What is the energy of the activated complex? Check, it's 100 over there. Right? What is the energy of the reactant? It's 10. So it's going to be 10 over there. And then how do we get here? We get 90 kilojoules. It means the activation energy was 90 kilojoules. So you needed to meet a certain, you need to go absorb from 10 and absorb 90 kilojoules for you to meet the 100. Right? The 100 is not the, guys, 100 is the energy at the activated complex. Then the activation energy is calculated like this. It's the energy of the activated complex minus the energy of the reactants. That's how you do it. Now, we'll speak about reverse reactions some other time. When we do papers, you don't need to know that for now. If you understand what I'm talking about here, you should be able to understand also what happens in a reverse reaction. Because in a reverse reaction is where you go for, okay, let me just say it. You go from products back to reactants. Now, everything you just did now goes back in reverse, right? Everything that you just did goes back to reverse. So your activation energy will be from 90 to 100 because you are going from, these are your new reactants basically if you look at the reverse reaction. So you go from here to the activated complex and suddenly you go there, because we said that from where you start to the activated complex, that's your activation energy. So for the reverse reaction, this right here, this small part would be the activation energy. So that's what I mean by when I saying but the heat of reaction will just remain the same. But you must know that now the final will be the reactant, the initial will be the product. Yeah, it's just you flip the roles around, right? That's reverse. It's just saying reverse. But guys, I would be explaining this when we do it separately, right? When you explain it separately, but don't worry about it. So now, just the consolidation of what we've been speaking about. Endothermic reaction, we absorb. One thing that I want you to take home is that the heat of reaction must be, or the enthalpy change must be positive, because we absorbed more. It means that the energy for our product was greater than the energy of our reactant. So when we minus to try to get the change, we must get a positive answer. I hope that one is clear, right? I hope that one is clear. And then the last one that I want to close off, I want you to know that an endothermic reaction makes things colder, makes things colder, or you can say makes the reaction colder. That is exactly what I want you to take home on this one. It makes the reaction colder. Please take note of that one. It makes things, or it makes the reaction to be colder. That is the ins and ends of endothermic reaction. If I forgot something, you'll try and remind me from there on. But now, what I want us to just think about is now go to our exothermic reaction. So from there on, I want to shoot straight to my exothermic reaction, right? Able to understand, okay, I'm bad at drawing these. I'm bad at drawing these. I don't want to lie. I'm so bad at drawing these. I can't, but I'm trying. Oh yeah, I'm not bad. I'm not that bad. How? Right? Exothermic reaction. Now understand one thing. We're going to do the same thing that we did just now. Right? Here, we're going to say reaction progress. Okay, let me fix that progress over there. Now, here I'll just say potential energy, then in brackets I'll just say kilojoules. It's fine, nothing will change. Now check one thing over here. We spoke about it exothermic, we spoke about exit, and we said over here we release. Over here we release. Now check one thing here. When we start our reaction, we're going to start off fairly quick with the energy of the reactant. Let me just start up higher, because there's something that will happen over here. Now, it doesn't mean this one starts up higher. Just don't do that. Yeah. So this one starts, then it goes, of course, it goes to maybe start, because you want to meet the activation complex, right? For you to start reacting, right? You start to go there, you go there, you go there, you go there. But you do what? You do what? You meet the activated complex, you go down, down, you don't stop, you don't stop, you don't stop, and then you go that way. Now, the same thing that we said will still remain over here. This is still the energy of the reactant. This is still the energy of the product. Now, this over here is still our peak that we called the activated complex, or activated complex. So the reaction gets activated. It's the activated complex, and we must understand that all the time when we go from where we start to the activated complex, we call that the activation energy. And you must understand that every time again, from the energy of the product to the energy of the reactant, that over here is the change in enthalpy, right? That's what you must know. The notes that you must be able to take out by yourself, right? Now check one thing. We spoke about a lot of energy releasing over here, or emission rather. We can use the correct English. Check one thing. Check one thing. Here, I will go and every reaction tries to meet the minimum requirement. What is the minimum requirement? The minimum requirement is always going to be the activation energy. So you need to meet the activation energy because every reaction wants to occur. So what are you going to do? You're going to try over here and go, okay, let me meet the activation energy. Let me meet the activation energy. Then you meet your activation energy. But we don't say that. We say you meet the activated complex. Once you meet the activated complex, it ultimately means that is the reaction, that is the activation energy that you needed for you to take for the reaction to occur. At the activated complex, the energy of the product, not the energy of the product, but the reactant will transition to what? To product. So over there now, you're going to be forming in a product. So everything else that you're going to be doing after the transitional zone, is just forming in a product. So if you go down over here, it's just you forming the product. But check, in the midst of you forming the product, you're actually releasing more than what you had at first. Because at first, if we start from here, and you say this is 20 joules and this is 10, check one thing. We start with 20 joules. What do we end with? With 10 joules. It means we released some of the energy, right? Because what are we doing? We're trying to meet the activation energy. I mean, to try the minimum energy required for us to react. And then after the activated complex, right? This is where the reaction occurs. This is where we can call it the transitional zone, right? They call it the transitional zone, right? This is the transitional zone. Why? Because it's where we transition or change from reactant to what to form any product, right? So if here we actually pass where we started, it means that we are releasing more than we had. So if you look at your change in enthalpy, if you check, make sure we say that it's going to be H final minus H initial. What is your H final, or the energy of the final part? The final part is what you produce, meaning the product. That's the way it says. The energy of the product is 10. And it's this one, 20. Now the what you find over there is negative 10 joules or kilojoules. I said energy is scalar. We don't use directions. If it's negative, this supposedly means that the activation, not the activated, but the heat or the change in enthalpy is going to be negative. Once they tell you that something of this nature is possible or it's there, just know that they are speaking about our exothermic reaction. These are just the basics, guys, that you must supposedly know. If the heat of reaction or the enthalpy change is negative, it means you released more than you already had. And I remember making this example and it sounded dumb, right? And I said 2 minus 3 going to give you negative 1. And I said this one doesn't have more to give, but it does give actually, and it becomes more negative. So even in this part, you have 20 joules, you start to give more, and then now you end up having 10. And then the change or the heat, which is basically what I'm crying about, because you must have a negative enthalpy change for an exothermic reaction. Just know the difference, because I don't want people to say, what is this? What is this? Because I just explained where it comes from. I know you can't grasp it one time. We are human, but it's all good. It's all fine. And the one thing, or the last part that I want us to take away, is that in an exothermic reaction, this one makes the system hotter. Makes the reaction, or it makes the system hotter. System hot. Nah? Why? Because it releases heat. We know that, right? This one will release the heat. right? Making it hotter. But for the endo, it makes it colder because it absorbs the heat, leaving everything to be cold. But now I want us to consolidate on everything that we just said. We said that for an endothermic reaction, we must know that this one means absorption, right? Absorption, and it means that over here the enthalpy change is positive, and over here we must understand that system get colder. The few notes that you must know. So here the absorption, you must know that over here it just means net energy absorption. Net means total energy absorption. So yes, we do release some, but yeah, we ignore it because basically we absorb more than we release, right? Making our change in enthalpy to be positive, right? So positive means greater than zero for those who don't do mathematics. Anything greater than zero is positive, anything lesser than zero is negative. There's another point that I want to put in here. They won't ask you that point, but yeah, let's leave it, guys. If you want to know that point, you can DM me on, I'll make you understand what is that point about. And if you're interested in physics like that, I'll take you on that journey. Now, the graph, you must be able to understand that it must be something like this, right? Why does it have to go to have an energy? The energy of the product, which is this part, must actually be higher than the energy of this one to show that we actually absorb more. And if it ends up lower, it means the enthalpy change will be negative, which is not true for an endothermic reaction. So that's why it ends up there. You must be able to understand this as the activated complex. You must be able to understand the energy from here all the way to the activated complex as the activation energy. You must be able to understand this as the heat of reaction or enthalpy change. So those are the things that you must supposedly know, because you have to be able to identify these things in an exam alone. Now, another consolidation that we have to speak about is an exothermic reaction, right? Is an exothermic reaction. Now, another exothermic reaction, another thing we must understand that over here there's a release of energy. There's a release of what? Of energy. Yes, there is some energy absorbed, but guys, check one thing. We release more than we absorb. So here we can say there is a net energy release. Yes, I know. Someone might say, yeah, in real life that's not true, but I just told you, yes, we do absorb some heat, but we release more than we absorb, so we can just ignore the other part. So here we release the energy. And also here there's another point that I'm supposed to add, but I won't add it because you know I won't say that, right? Yeah, I said you can DM me for that one, right? You don't even ask you in an exam, but it's just for curious people. You can come in and come to me with that one. Now here this one will be negative. What? Because we must know that the energy of the product, like the energy of the product, right, is actually lesser than the energy of the reactant. So if that happens, we're going to get a negative answer, right? Because for change, we are going to be seeing energy of the product minus energy of the reactant. So if the energy of the product is smaller than the energy of the reactant, we're going to get a negative answer because we're going to be seeing smaller number minus bigger number, which is something I should have put over here to see that over here, the energy of the product is actually greater than the energy of the reactant. So if that is true, it means that we're going to be minusing a bigger number from a bigger number, meaning that going to be minusing a smaller number from a bigger number, which is just going to be positive. So that is just mathematics over there. Yeah, it's going to come, don't worry. All at the right time, don't worry, right? So here, that is what you're supposed to know. And then another point that I'm supposed to put, am I forgetting something in terms of the consolidation? Yep, yes, that point that over here, this one, systems get hotter. Systems get hotter. Systems get hotter. Now, this is the in and in of endo or exothermic reactions. There's nothing else that you must know about endothermic reactions. There's nothing more you must know about exothermic or endothermic reactions. This is all that you need to know. When we meet, we're going to be understanding the factors and using the collision theory to explain all the factors that affect the reaction rate, and then we'll be able to go from there on. Thank you.